continuing on from what I was talking about with gravity being energy gradients and magnetic fields being basically a lack of energy, magnetic cooling is proof that magnets are just creating points of low energy density. Ferromagnetic material that solidifies or freezes when introduced to a magnetic field is basically proof of this, right? Because this material literally goes from being a liquid to a solid when a magnetic field hits it. And so to me, that is saying there is less energy in a magnetic field than there is outside of one, right? And the fact that you can use magnets to cool things down, and magnets are used in laser cooling as well. It's a combination of lasers and cooling, lasers and magnets to cool down these things to absolute zero. You do it in magnetic fields, and I think that this is, basically definitive proof that they are just points of low energy. And again, this material that is capable of going from a liquid to a solid as soon as it's in a magnetic field is kind of, in my opinion, definitive proof of this as well. But moving on to the next thing that also kind of has to do with this is I believe that radioactive materials are radioactive due to the low energy density they are within. I think that if you were to place a radioactive material in hot conditions, hot being, relative here, it would decay slower. The problem is that the only materials we could test this on and see effective results would need to have very slow half-lives, as that would show they are more compatible with low temps and more likely to be stable in high temps. So what I'm saying there is basically, every material is basically, our universe is pretty cold. In the grand scheme of things, the majority of the universe is quite cold. And because of this, things that are, a lot of stuff is solid. A lot of matter is solid. And there's also a certain amount of this, like after lead, I think lead is like the last one. After lead, things become radioactive and then decay over time. And I think the reason why they decay over time is because there's not sufficient energy for them to maintain their structure. And so, they run out of energy slowly over time and decay to a particle that is of sufficient energy, which tends to be, whatever is next down, or slowly works its way down, and a bunch of materials end up at lead because lead is still good. It's still, stable at, quote unquote, room temperature, I guess, or like the universal temperature. We don't have to do anything to keep it from, decaying, like having this radioactive decay. And there are materials that have extremely long half-lives but do slowly decay. And so what we would assume is that materials that have extremely long half-lives, right, are probably just on the verge of where, our current universe's temperature is too cold, right? And so I don't know exactly how much energy is needed to be considered hot enough, right? But my theory is that if you did heat up these materials to potentially, higher temperatures, right, then they would decay less. And I don't know, maybe I should have done some searches on this. I don't think heating a material up causes it to decay more, which, a part of me feels like, from a logical standpoint, maybe heating something up should make it decay faster because it moves around more and it's doing more, which means that, if it was, decaying because of just some inherent randomness, you think that randomness would be increased over time, with it being able to have more free motion or something along those lines. And I'm not sure if that logic tracks. I realize that I probably need to do a little more digging into the mechanics of decay to understand exactly what we believe the reasoning for decay is. Because I know it's the weak force, but I don't remember what is the reasoning behind it. Like, is it just random? I don't, maybe it is just random. I don't know. But I don't think that it is just random. I think that when an atom runs out of energy, it goes, crap, we don't got enough energy, and it allows for the release of helium. And I talked about why helium is something that can be decayed out of an atom pretty easily, and why it's a very common thing to see. And so basically it runs out of energy. Its gravitational pull is not enough to counteract thing like a helium atom forming within itself. And so when a helium atom does form, boom, it gets shot out, right? And then that's what we call, like, that process taking place over a long period of time. That's what we consider, the half-life. And for materials that are more radioactive, that half-life is faster. And so I think it would be interesting to see if we could see, a change depending on the temperature. And I think I looked it up, and they said there's no proof proving that heating up a material has an effect on its radioactiveness, but I don't know. And I don't know if we could potentially test it, but I also feel like it would take a lot. It would require high amounts of energy, and it would require a lot of time to get effective results. And you'd probably have to do it multiple times. So I don't know if it's necessarily the most economically and energetically feasible experiment. And I don't really know, like I said, what the temperature would have to be, because maybe it needs to be a gas for it to maintain stability. I don't know, right? Like, if like uranium or plutonium needed to be in a gaseous state in order for it to not be radioactive, that would be kind of interesting, but I don't know if that is true. And I feel like some of these experiments could be extremely dangerous considering it's radioactive material. So I really don't know if it's worth it to try and, experiment with some of this stuff, because, it's risky business. But I am curious about if that is potentially something we could prove, and if we did prove that, what that means for, these processes, because higher energy leads to a more stable material, would also lead to, in my opinion, the conclusion that materials are consuming energy, and that would be, a victory for my theory here, basically. And as of right now, the firm belief, I just watched a video talking about the Navier-Stokes equation or whatever. I feel like I might have pronounced that wrong. But the guy kept saying, but it's conservation of mass. It's conservation of mass. It's conservation of mass. He said it so many times. Like, it can't be wrong. Like, there's no reason to conclude that conservation of mass is wrong. So, like, it's not the equations that are wrong. It's got to be the mathematical understanding that's wrong. It can't be these. Like, there's no reason to conclude that these are wrong. And I don't know if conservation of mass is as fundamental as we think it is. And things like seeing decay, radioactive decay take place, would also lead to, like, it's not that the matter's being destroyed, right? But it's being converted or transformed into other things. And so when you're looking at a conservation of mass, right, and you have things like an atom decays, right, and then you have the neutrino and all this stuff. Like, are we considering the neutrino now like that mass has been maintained, right? That energy is still maintained in this neutrino, but like, is it like, are we gonna ever get that mass back from that neutrino? Like, neutrinos are very rarely interacting with any matter, in general. So I feel like saying that neutrino, oh well, it still has mass though, so it conserved the mass, right? The mass has been conserved, but I don't know if that really is as sound an argument as you think it is, because I mean, I'm not saying that the energy in the matter has been just poof, it's gone, but it's converted into something that is basically no longer useful. It's no longer valid. And, so it's almost like saying that, if you have a bucket of hot water and then it cools down, right? And then it turns into ice, and you say, oh, but it's still, the heat was still conserved, right? So it's fine. Like, we still have, like, heat was still conserved in our equation. So even though our bucket is ice, heat was still conserved. There's I don't feel like that's really an argument to make, because yeah, it was conserved in the sense that now the atmosphere took in that energy, but you've got a bucket of ice now. So your system that you are working with has not conserved that energy. Right? So what I'm getting at is that in the grand scheme, it's conserved, right? But just because it's conserved doesn't mean it's still useful and fundamentally the same. Because we have things like I've talked about dark energy and dark matter, right? Dark energy this is my theory, basically. Dark energy becomes matter, matter becomes dark matter, right? And so energy is conserved through this process, but saying you have a piece of dark energy compared to a piece of matter, they're fundamentally not in the same classification for a reason, right? So saying all of your mass has been conserved as dark matter is kind of silly, because, that's great. You still have your mass conserved. It's conserved. It's over there. But what are you going to do with it? You can't touch it now, right? And I feel like I went on a pretty big tangent there, and that was such a niche little side thing that I don't even think it really needed to be in this one. But anyway, basically, long story short, I think it would be interesting to see if we could prove or disprove. I don't know if we can disprove, but if we could, the ways to disprove my theories is basically either heat it up to a really high temperature so it doesn't decay, or cool it down to such a low temperature that it does, right? If either of those two things happens, you know that I'm right. And I'm kind of curious in the experiments where they cool things down to so close to absolute zero. I'm kind of curious to see, are they observing what is happening to these materials? Are these materials decaying at these cold temperatures? And is anyone looking for that? I feel like they would have to be, observing for these sorts of things, just with the instruments involved in such complicated processes to cool these materials down. But I don't know. It depends on what materials they're using. Maybe they're using material that is pretty chill, and it wouldn't decay at that temperature. But if they did it with a heavier, more dense material, it would. And they just haven't done it with a material that could do that or would do that. I don't know. But I also don't like. I'm also like, I don't know if I really want to encourage people to do that. Like, deal with very small quantities of material, because if you do it with a large amount and you accidentally make some kind of nuclear reaction, right, and you have like a mini atomic bomb go off because you're doing this experiment, like be very careful with this, because I don't know exactly what would happen if you were able to basically achieve this spontaneous decay. Like, if you were to achieve a spontaneous decay, I have a feeling that it would release a lot of energy. I just don't know how volatile it would be. So be very careful with this, because like I may be totally wrong about this, but it's better safe than sorry. So like, you know, don't do that. You know, I don't know. Just be very careful with the with that. And like one thing I'm concerned about is like, we're trying to achieve this absolute zero, and if I am right, and people are just kind of, they don't think anything's gonna happen, and then something does because we don't know, right? That's gonna be not good. So, you know, maybe, you know, try not to F around and find out, you know, if you know what I'm saying. Anyway, peace out.